Hey class, this is Mr. Schmidt for the Halloween version of our pumpkin drop. So this year, remember, you're treating your pumpkin like a cylinder in order to do some of the measurements, approximate the measurements, and we are putting it inside a device and dropping it from a height. Okay, so I had two different pumpkins I dropped from the top of Skyview, and you can see that on the neighboring video. Okay, um, with this, I had all the measurements, and this is the one we're going to be using for our measurements here today. Remember, we still have all the same choices we've always had for our equations as we go through these calculations. Okay, when I did this, I took it through the graphical analysis of video physics, Veneer's video physics. Okay, the good thing about this was this gave me the time for the entire process, which was very close to 1.5 seconds. Okay, we could also look at the angle and the slope to figure out some of the other numbers, but we're going to just take it for what it is. Okay, so with that, we're going to turn our page. We're going to go over to here and get started. Okay. Okay, so I've inserted in my time off of the actual measurement. Okay, everything else was also measured prior to drop. Okay, so what we're going to do is we're going to work our way down here. Once we have these numbers, hopefully that can help us solve for this time. This is going to be a solved number because we were never inside the box to see it drop. Okay, and then we'll solve for these remaining numbers. Okay, remember this is an engineering challenge, so we're only trying to find the engineering solution. We're not going to write up a full lab for this. Okay, all right, so our first goal here is to find the velocity. Okay, so let's take a look at this and the velocity. Okay, so we know the kind of fundamental definition of velocity is that, but that is for the average, right? Okay, so now we want to be able to find the final. Okay, so we're going to take these numbers and put them in here for 1.5 seconds. Okay, 11. Okay, so that gives us our first number here. Okay, try not to round at this process. We're going to be doing a lot more steps. Eventually, we're going to take it down to just a couple significant figures in our final answer. Okay, all right, so that was the average. But remember, we would have to multiply this by 2 and technically add in our initial, which was 0. Okay, so we're going to multiply that by 2. All right, and so our V final equals 14.66. Okay, so that goes in over here. All right, so now we have our final velocity, we have our initial velocity, we have time, we have distance. Now we can solve for acceleration. Okay, there's a number of ways we can do this. I just like sticking with the fundamental equation if I can. Okay, so this went 14.66 meters per second in 1.5 seconds. Okay, and so that was, all right, so that gets us pretty close to, oops, let's get rid of some of this. All right, so not quite 9.8, but awfully close there. So not too much air resistance in this process, okay? So hopefully that's what we're saying, just under 9.8 is your number. If you had balloons or parachutes or anything like that, then this number would go way down, okay? All right, so now on to force. So our mass was 0.795 okay? You absolutely have to have everything in meters, seconds, and kilograms, okay? I know some of you are going to be using tape measures to do some of this in inches. You have to convert to meters before you can go into any of your calculations, because what we're trying to solve here is newtons. Okay, so then we get, okay, this whole thing, remember, that is also newtons. Okay, so now we can go, okay, so that's why we need to have those units. So we can just write this down as newtons. Okay, and then our pressure over the striking surface okay, so now we have, all right, this is the point I'll start thinking about rounding here. Okay, we could call this pascals or newtons per meter squared. Okay. All right, so that takes us all the way through here, which should give us some useful pieces to find out how much time is that compressing inside the box. So now we know over here that the velocity of the box and the pumpkin inside it was the 14.66. Okay, so now within this distance, it has to go from 14.66 meters per second to 0 meters per second. Okay, and as you saw on the big pumpkin, if we shrink this distance down to like 0.01 meters, we get a colossal big explosion of a pumpkin. Okay, all right, so let's keep going here and look at the other side of the page. Okay, so now we have some choices and some questions here because there are a lot of ways we can solve for time and acceleration, but the hard part is knowing what's happening here. So first of all, let's remember this velocity was 0. Okay, so that was already set. Okay, so now we can use two velocities and a distance and try to solve for time or try to solve for acceleration. Okay, so one way we can do that is x equals x naught plus v average times time. The other choice we have, remember, we don't want an equation that has time and acceleration in it. We need one that's just acceleration, I mean just time or just acceleration. Okay, so we can solve either of these independently, and we're going to find out if we solve one, we'll either have another choice to solve another. So let's start with one of these and see how we go. Okay, so if we have 14.66, well, at one point we even calculated what the average was, plus 0 over 2 equals, so this, I'm trying to figure out V average. Okay. Okay, so an average inside the box, assuming it had linear compression and linear deceleration, this was our average. Okay, so that number can now go in here. Okay, so it started at this height. It had, this was going down. Okay, so it ended up on the pavement. It started this high up. Okay, that's how high before the padding started getting compressed. Okay, but it was going down at this speed. Okay, and we're trying to solve for time. Okay, so we can subtract it over to the other side. Okay, and we get 0.095 divided by 7.33. Okay, so talk about a little bit of time here. 296. We'll carry this out for a little bit. Okay, notice a lot of these numbers are going to get eliminated. I just don't want to keep chopping off numbers that have a little bit of meaning right now. Okay, so that equals our time. All right. 1, 2, 9, 6. All right, so now we know the time. We could do a number of different equations. All right, I'm going to solve acceleration one way, this way, and then we're going to use time, and we can find out we get the same number another way. Okay, so again, same numbers here. Okay, we end up at 0. We started at 14.66. Okay, and we want to find that number. I'm just going to leave it as a different color for a moment to remind me I don't know what it is yet. Okay, and it changed a distance of 0.095. Okay. All right, so now we can go back through and do our calculations. All right. Divide by 2 and divide both sides by 0.095. Okay, remember when you do this, make sure that's in parentheses, so you're dividing by all those numbers. Okay, that was a comma there. Okay, a very big number. All right, so that is one way we could solve it. All right, now let's try to think about another way we could solve this. We could have also, so this was one solution here. We could have also have done d equals okay. We could have also solved for it this way, where we again had 0 plus equals, and our velocity going down, and our time, plus, send that over here, half a okay, and what do you know, our acceleration once again is, so in this case I was calling that negative, so we have our 1, 1. Okay, now let's say you want to be very thorough. This is a review video here. What happens if we just wanted to do acceleration equals our change in velocity over our change in time? Okay, well, we still know our different velocities. Okay, and we still know our change in time. Okay, every time. Okay, so there's 3 different ways we could get the same number. Okay, so that's good news. That means we are following along the same way here. All right, that also means you have some choices when we come to any type of quiz or anything like that. Okay, so they all return the same velocity here. Okay, now force, hopefully this is starting to get redundant here. F equals ma. So F equals the mass of the pumpkin times our acceleration. Okay, so once again, we plug that in. Equals 7, 7, 7. That's a cool number. All right, so that was our force. Wow, okay. Not at all what I planned. All right, and then our pressure equals our force divided by our area. Okay, and this was, and our area for the cylindrical bottom of the pumpkin. All right. So, anyone surprised that the pumpkin did not make it? Okay. All right. So, that is how much force was applied to the pumpkin here. Okay. All right. So, hopefully now you've seen what's going on. All right. And you can answer a few short questions here. Remember, do this part by yourself, or excuse me, do this part you can do with a group, do this part you can do by yourself. Please include your calculations, also any videos or graphs or pictures, much be appreciated. Okay, and with that, have a happy Halloween and a safe weekend, and I'll see you all next week.